All right, this is chapter 42, nuclear physics. We're done quantum physics, so you should all be rejoicing. All right, nuclear physics. To learn about the size and structure of the nucleus. To learn about the properties of the nuclear strong force. We're going to apply and interpret a simple shell model of the nucleus. So once again, we make a model, right? And this is the shell model. It's pretty good. To understand radioactive decay and half-lives, to learn about radiation dose and biological applications of nuclear physics. Okay, every time I teach this, a lot of students say, why do I care? So I want to spend some time convincing you that you need to learn a little bit of nuclear physics. All right, because there's lots and lots of applications of nuclear physics. Okay, plant mutation breeding, fertilizers, insect control. Let's talk about insect control. Sterile insect technique, SIT, right? A method of biological mosquito control. All right, so they breed a ton of mosquitoes. So mass rearing of mosquitoes takes place in special facilities. So they breed all these mosquitoes. And then, I don't know how, but then it says male and female mosquitoes are separated. And then they use radioactive materials, ionizing radiation, and they sterilize the male mosquitoes. Then the sterile male mosquitoes are released over towns or cities. Oh, great, right? Well, hold on. And of course, where they compete with the wild male mosquitoes to mate with the females. When the sterile male mosquitoes mate with the female mosquitoes, these females lay eggs that are infertile, and they bear no offspring, reducing the mosquito population and the disease transmission. All right? So they expose mosquitoes to radioactivity, and it sterilizes them. Okay. Consumer products, food irradiation. Later. Industrial tracers, inspection and instrumentation, carbon dating, desalination. Medical diagnosis, oh my gosh, all over the place. So medical applications of nuclear physics. Cancer, treatment, computer imaging, radiocarbon dating. I wouldn't really call that medical. Just like a smoke detector is not really medical. Whatever. Food irradiation. So that's how they kill some of the bacteria and stuff. Radioactive tracers, I-131 is used to treat thyroid illnesses. Thallium-201 can be used to determine damage done to somebody's heart by a heart attack. These are radioactive. I-131 and thallium-201. Medical therapy, sterilization, supposed to be of medical products and supplies, nuclear-powered ships, nuclear reactors for electricity. By the way, what's this? So it's horrible pollution, right? No, it's just steam. These are called cooling towers. It's just steam, right? So if you ever see something like that, don't think, oh my gosh, I'm polluting the world. It's just steam, right? They just shoot hot water up here and they cool, and then it's steam. Let's see, nuclear reactors for space, hydrogen, electricity in cars, environmental tracers, water resources, tracers. Oh, this is kind of funny. The first practical application of a radioisotope was made by a Hungarian man named George de Hevesy in 1911. At the time, de Hevesy was a young student working in Manchester, studying naturally radioactive materials. Not having much money, student, he lived in modest accommodations and ate his meals with his landlady. He began to suspect that some of the meals that appeared regularly might be made from leftovers from the preceding days or even weeks, but he could never be sure. To try and confirm his suspicions, de Hevesy put a small amount of radioactive material into the remains of a meal. Several days later, when the same dish was served again, he used a simple radiation detection instrument, a gold leaf electroscope, remember we talked about that, to check if the food was radioactive. It was! and de Hevesy suspicions were confirmed. History has forgotten the landlady, but George de Hevesy went on to win the Nobel Prize in 1943 and the Atoms for Peace Award in 1959. His was the first use of radioactive tracers, now routine in environmental science. Ha! All right, so all I'm saying, gosh, there are just so many uses of radioactive materials. It's just amazing. Okay, so let's talk about the present understanding of the nucleus. Here we go. The nucleus is a small, dense, positive core at the center of an atom. You already know that, right? Because the nucleus is made out of protons and neutrons. Neutrons are neutral, that's why they're called neutrons. Protons have a positive electrical charge, so therefore this whole nucleus has a positive charge. Okay, now here's some things that you may have not seen before. So what we're going to use uppercase Z for the number of protons, okay? Just Z, I don't know why, but Z, right? Number of protons. And of course, a proton has charge plus E, where E is the charge of the electron. And don't worry about that. We haven't talked about that yet. Neutrons have 0 charge. Don't worry about that. Okay, now the mass number, they use A, right? Okay, the mass number is A, and it's just the number of protons plus the number of neutrons, right? I mean, think of an atom. Where's all the mass come? You know, the mass of a proton, the mass of a neutron is, you know, much, much, much larger than the mass of an electron. So all the mass of an atom comes in the nucleus. So it kind of makes sense that the mass number is the number of protons plus the number of neutrons, right? Okay, this is just an experimental result here. The nuclear radius is R, and this should be approximately equal to R0 times A to the 1/3. So here's this A, right? So the nuclear radius is approximately equal to R0, A to the 1/3, where R0 is 1.2 fermis. What's a Fermi? Or some people call it a femtometer. Fermi is better, because it's in honor of Enrico Fermi, a famous physicist, right? Typical radii of a nucleus are a few fermis. What's a Fermi? 10 to the minus 15 meters. So a nucleus is really, really small, right? Really, really small. Okay, so this is this is the important thing. Well, I mean, it's all important, but this is super important, right? Mass number is A, number of protons plus number of neutrons, Z plus N. All right, and just kind of want to remember this too. A Fermi is 10 to the minus 15 meters. Okay, this is cool. This picture, all right, so here's a picture of an atom, right? So here's this atom. Here's the nucleus. Then the nucleus again is protons and neutrons, right? Okay, oh, here's another term. So sometimes, instead of saying protons and neutrons, some people just use the word nucleon. So nucleon is either a proton or a neutron. I mean, you know, nucleon, nucleus, you know. All right. All right. Now look at these numbers. So an atom is about 10 to the minus 10 meters in diameter. Nucleus, I mean, you know, it depends how many nucleons, like, you know, a certain number of fermis, right? So let's say 10 fermis, 10 minus 14 meters. All right, so 10 to the minus 4, 10 to the minus 14. What's the difference? What's the difference? Well, 10 to the 4th, that's 10,000, right? Okay, this picture of an atom would need to be 10 meters in diameter if it were drawn to the same scale as the dot representing the nucleus. You get that? So that means if we wanted a scale drawing of an atom, if this represented the nucleus, then the atom would be 10 meters in diameter. 10 meters! That's pretty big. Okay? Okay, so here's another way of looking at it. All right. This is the modern atom model. Electrons are in constant motion around the nucleus. Protons and neutrons jiggle within the nucleus. And we now know that there are smaller things than protons and neutrons. They're called quarks. So quarks make up protons and neutrons. Quarks jiggle within the protons and neutrons. Okay, so there you go, right? So here's the electrons, you know, and here's the protons and neutrons, because these are the quarks. Quarks make up protons and neutrons. Okay, here's the cool part. This picture is quite distorted. If we drew the atom to scale and we made protons and neutrons a centimeter in diameter, then the electrons and quarks would be less than the diameter of a hair, and the entire atom's diameter would be greater than the length of 30 football fields. So in other words, okay, I got to get this right. Okay, in other words, 99.99999999999% of an atom's volume is empty space. Huh? Is that cool or what? You know? And that's, so basically an atom is primarily empty space, right? Okay, so that's kind of interesting. I hope you understand that. And again, just, you know, look at the numbers, right? This is 10,000 times that, you know? Right? So there you go, right? A centimeter, protons and neutrons, and the atom, 30 football fields. Those are U.S. football fields, by the way. Okay, let's talk about something called an isotope. So here's my physics joke. So most of the atom is empty space, right? Okay, so now as in college, you know, if you want to insult somebody, you say, you airhead, right? You use that term, airhead. And that's wrong, right? Because we're mostly empty space. So you should not refer to a friend as an airhead. You should say that the person is a space cadet, meaning empty space. All right, sorry. Okay, let's talk about something called the isotope. Isotope. How many protons are in carbon? So how many protons are in carbon? 6, right? So carbon has Z equals 6. 6 carbons. Well, great. Okay, now here's something from a book I have. Now look at all the different kinds of carbon. My goodness. Carbon 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It's all sorts of carbons. What's the deal? I mean, what's going on here? I thought carbon was carbon. I mean, what do we usually have? You know, we usually think of carbon 12, right? That's carbon 12, you know, carbon 12. But wait a minute, it doesn't even say 12. It says 12.0112. What's the deal with that? So just so look, this is nuclides and isotopes. So this is the chart of the nuclides. All right, so there's all these different carbons. So what's going on? Well, isotopes, what it means is the same Z, but different N. All right, so all of these carbons have 6 protons because that's what makes carbon carbon. But they have a different number of neutrons. So here, carbon 8. So these numbers here, the 10, you know, these numbers here, that's the A, the number of protons plus neutrons. So carbon 8 has 2 neutrons. Carbon 9, 3. Carbon 10, 4, and so forth. Carbon 12, okay, 6 protons plus 6 neutrons. All right? So this is the most abundant carbon, carbon 12. Yeah. So isotopes, all right? I mean, look at them. Beryllium, you know, has a bunch of different types of beryllium, all sorts of things, you know. Look at all different forms of helium, just different numbers of neutrons. So when you look at the periodic table, you know, just an ordinary periodic table, you know, 12.0112, you know, what's that? It's a weighted average. It's a weighted average. So that means that they look at the abundances of all the isotopes and they make an average, right? A weighted average depending on how abundant they are. That's why it says, you know, 12.0112, rather not just 12. Okay, so you know what isotopes are, right? Same Z, different N. Okay, when you do nuclear physics, whatever reason, they have their own system of units. So whatever, you gotta do it, you gotta do it, right? And so the atomic mass of carbon-12, 6 protons and 6 neutrons, right, is equal to 12 U, okay, U, right? And this is a U. Now look at it, we're using relativity, right? Remember E equals mc squared? That means m equals energy over c squared. So there you go, 1U equals 931.49 energy divided by c squared. So we're going to use that routinely, right? We're not going to use joules very often, right? We're going to use electron volts, kilo electron volts, million electron volts. So make sure you know how to do that. And we're going to use relativity, right? Mass is energy over c squared. Okay, so that's cool, right? Okay, let's see. Yeah. By the way, if you want to know, sorry. Okay. All right. You can also, here's another way to say U, but I don't want to do it. I never remember this because I never use it. Okay, that's another 1U equals 1.66 times 10 minus 27 kilograms. Who cares? Again, it's more convenient to use energy units. So we'll always use that. Okay, let's talk about the density of a nucleus. The density of a nucleus. All right, again, this is an experimental equation. This really should be approximately equal to, but whatever. All right, so we want to calculate the density, all right, of a nucleus. The mass density. So density equals mass over volume. No kidding. All right? And what's the mass? Well, it's the number of nucleons, which is A, times the mass of a nucleon, which is a U, right? So the number of nucleons is A, and then we're saying that the mass of a nucleon is U. Remember, carbon-12, right? We said carbon-12 had a mass of 12U. So we're saying that a nucleon, so the mass of a nucleon, which is a proton or a neutron, is U. Now that's actually incorrect, but it's close enough for right now. All right, we'll discuss why it's incorrect later on. I mean, basically, the mass of a proton is not equal to the mass of a neutron. It's slightly different, but it's super close, so we're just going to keep this for right now. All right, so the mass, so this is the nuclear density. So the nuclear density is the mass of a nucleus divided by the volume of the nucleus. The mass of a nucleus is the number of protons and neutrons times the mass of a proton or neutron divided by the volume. Well, we're going to say it's a sphere. It kind of makes sense, right? So 4/3 pi r cubed. All right. And then we have this thing. All right, so it's A times U. That's A times U, right? Okay, so I have 4/3 pi. Now, what's R? It's right here. So we have R cubed, so we got to cube that thing. So we have R0 cubed, then A to the 1/3 cubed is just A. So we just get A. But then, of course, the A's kill. So we get U over 4/3 pi R0 cubed. Now, if you want to, you can write that as 3U over 4 pi R0 cubed. Okay, now wait a second. 3 is a constant, U is a constant, 4 is a constant, pi is a constant, R0 is just 1.2 Fermi, so that's a constant. So this is, guess what? Constant. So basically what we just proved is that I don't care what isotope you have, uranium, hydrogen, zirconium, technetium, whatever you want, the nuclear density is basically the same. Okay, basically the same. Now, let me just explain what I said earlier. So here we just said that the mass of a nucleon is U, and that's a little bit wrong. The mass of a proton is actually 938.272 million electron volts. By the way, I mean, we should really say MeV over c squared. We don't usually bother with the c squared because it's understood, okay? I mean, get used to it, all right? But it should be there, but we don't bother. And the mass of a neutron is a little bit heavier. And you'll see why later. 939.565 MeV per c squared. So, you know, it's like 0.14% difference, okay? But anyway, oh, that's a neutron. Sorry. Okay, so the neutron's a little bit heavier than the protons. Not much, but a little bit. And we'll see why later on. Okay, now how did we come to this understanding of atoms and neutrons, I mean nucleus and the nucleus and all that? So this is just a little super short history lesson. Okay, in the late 1800s, we had what was called the plum pudding model, okay, of the atom. The plum pudding model of an atom. And so that's plum pudding. It's kind of like fruitcake, you know? That's what I think of it as anyway. And so what the plum pudding model was, here's another plum pudding model, right? So basically, so they knew about electrons at the time, but that's it, right? So they knew about electrons, and they knew that the atom was neutral most of the time, you know? And so what they said, you had this sphere, right? And like the sphere, like was sort of, you had all this positive charge like smeared out all over the place, but you had these little negative guys here and there. So that's what I mean. Look at the plum pudding. So just imagine that the pieces of fruit are like the electrons, and then the bready pudding stuff is like positive charge. Okay? Again, they didn't know about protons. They didn't know about neutrons. And so that's why the positive had to be like just kind of all over the place. But then they had these little pieces of negative fruit or negative electrons, you know? Right? So that's the plum pudding model, okay? It's a sphere of positive charge with these little negative guys here and there. All right? Okay. Well, you know, you got to test your models. And so there was a very famous physicist from New Zealand, Ernest Rutherford. In 1911, he did what's called now the Rutherford scattering experiment. All right, so here's a piece of a thin gold foil. So just think of the plum pudding, okay? And he used a radioactive source to shoot alpha particles. Now this doesn't mean anything to you right now, but it will. But just think of it like this. Here's a piece of foil. Think of the plum pudding. Think of these as little tiny bullets. So they shot these little bullets at the plum pudding. Now, come on. What do you expect is going to happen when you shoot bullets through something like that? Well, the bullet's just going to go straight through, right? And that's what they expected. They just expected the alpha particles, the bullets, to go straight through. Well, they were shocked, totally blown away, because look what happened. Instead of going just straight through, or maybe just with a little tiny deflection, you know? But instead of that, look, there's these huge deflections. Look at that. And crazy, right? So they were totally blown away by this experiment. Totally blown away. And, here's a famous quote. You get this in every physics book that I've ever seen that talks about this experiment. So this is Rutherford. He said, "It was almost as incredible as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you." So that's what I mean. They were totally blown away by this. All right? So, well, what does that say about the plum pudding model? It needs to be revised, right? It needs to be revised. So they came up with a new model, which is called the planetary model, which is what I learned in high school. Hopefully you didn't. Hopefully you learned a more modern version. But anyway, this is the planetary model. So the planetary model has, there has to be these super hard, dense things, a nucleus, right? There has to be these super, super dense things, and they carried all the positive charge. They didn't know about neutrons yet, right? So we have these incredibly dense, tiny, positive things, which was what they call the nucleus. And so when you had the bullets coming in, sometimes they deflected, right? Sometimes they just go through, but sometimes they would deflect because they were so, like this guy, look, here comes the bullet, smack, then it goes back like that. All right, so that's the planetary model, okay? And yeah, they also said that the electrons they orbit this nucleus. Okay, so that's great. So all right. So that experiment was done in 1911. The neutron was discovered 1932. Wow, 21 years later. Incredible. All right. In the 1970s, quarks were discovered. Remember, a quark makes up protons and quarks make up protons and neutrons. And here's the quarks. So there's 6 types of quarks: up, down, charm, strange, top, bottom. And look, they have fractional electric charge. Fractional electric charge. They come in different varieties called colors. All right. Okay, here's another physics joke. Sorry. So my PhD experiment, we learned a lot about the charmed quark, a ton about the charmed quark. And so I had a very charming experiment. Pretty sick, pretty sick. All right. Quarks are confined to distances less than 10 to the minus 15 meters. Think of the Heisenberg uncertainty principle. If they're confined to within 10 to the minus 15 meters, what's the uncertainty in their speed? Well, basically, they go almost to the speed of light. So really, to discuss quarks, you need special relativity. All right. So if you want to understand the nucleus properly, you're going to use quantum physics and special relativity. Don't worry, we're not going to get that much into depth. Okay. Oh yeah, here. This is kind of cool. A proton is made of 2 up quarks and a down. Okay, so up has charge 2/3. So you have 2/3, 2/3, and a down has minus 1/3. So 2/3 plus 2/3 is 4/3. Minus 1/3 is 3/3 or 1. Okay? On the other hand, a neutron is a UDD, so up and 2 downs. Up is 2/3, the downs are minus 1/3. So 2/3 minus 1/3 minus 1/3 is 0. All right? So it all works. That's all I'm saying. It all works. And we discussed the discovery of the top when we did relativity, remember? Remember those protons and antiprotons annihilating and then creating these gigantically massive top and antitop quarks equals mc squared. Okay, now let's talk about stability. So here's the neutron number, the number of neutrons. Here's the proton number, number of protons. And so this line here is the n equals z line. So everywhere along this line, the number of protons equals the number of protons equals the number of neutrons. And you can see that, when you get small z, this is the data, right? The blue is the data. And so down here, for most of these isotopes, the number of protons equals the number of neutrons. But then you see that it starts going like this, right? Okay, now, stable nuclei cluster very close to this line. So we're going to call this the line of stability, all right? What we're going to learn is that most nuclei are unstable. That means that they don't last very long. They decay. We'll learn it, and that's called radioactivity. The stable ones follow this line, which means that they have more neutrons than protons. So you see that and say, why? Why does having more neutrons make the nucleus more stable, right? Has to be a reason, Okay, unstable nuclei are on are in bands along both sides of the line of stability. So these are all isotopes, right? These red lines. These are all isotopes that are unstable. They're radioactive, which we'll talk about in gory detail. So we look at that and we just have, wow, what's going on? I mean, number one, why does this line of stability deviate from the n equals z line? Why are more neutrons necessary for stability? But look at also this. Why aren't there any stable nuclei after bismuth, right? So we have Z equals 83 and no more stable nuclei. Why? What's going on here? So when we come up with our model of the nucleus, we've got to explain all that, And we will. Don't worry, we will. Okay, let's talk about binding energy. Binding energy. So here's a car. All right, now, so let's say I measure the mass of the car, and I'm doing it very carefully. So I get the, so I measure the mass of the car. Very nice. So I get the mass of the car. All right. Then I have some free time, and I take it all apart. All right? So I take it all apart, and I don't lose a single piece. And I use the same measuring instrument that I used when I measured the car. And we're saying that they're very accurate. Okay? So then I measure every little piece, right? And I add them together. So I have now the mass of the pieces. Okay? And I sum them up. Now, if I didn't lose anything, and if the measuring device is correct, what would I say? Well, it's sort of obvious, right? It better be, I didn't lose anything. So the sum of the masses of the individual pieces ought to equal the mass of the car. No kidding. Wow. Do the same experiment with a nucleus. So measure the mass of a nucleus, and then measure the individual pieces of a nucleus. Okay, so do that. And what would you expect? Well, classically you'd expect, what would you expect? So this is what you get. The mass of the separated nucleons is greater than the mass of the nucleons. That's like saying this, right? That's like saying that the mass of the pieces is greater than the mass of the car. That's weird, right? That's weird. How do you explain that? Well, it takes, remember, the nucleus is stable. We're going to say we're only working with stable nuclei. So the nucleus is stable. And if you want to break it apart, it takes energy, right? It takes energy to bust the nucleus apart. And so what we're saying is that the energy of a nucleus is less than the energy of the individual parts. And remember, equals mc squared, right? And energy is equivalent to mass, all right? So the nucleus has a smaller energy than the separated parts. And nature favors low energy states, remember? N equals 1 state for atoms, N equals 1 state for molecules. Low energy states are favored, okay? So the nucleus has a lower energy than the separated parts. All right? Now, if you want to bust apart a nucleus, you have to have energy greater than what's called the binding energy, okay? So the minimum energy needed to bust up a nucleus is called the binding energy. So look, so here's a nucleus, and here's some kind of energy, and we're going to say that as B for binding, right? Right? So the binding energy is the minimum energy that would be needed to disassemble a nucleus into individual atoms, right? So if the energy is greater than the binding energy, there's a nucleus, and bang, you smash it up, right? So energy what's the energy of a nucleus? mc squared, right? Rest energy of a nucleus. So binding energy plus rest energy, mc squared, and here you go. Energy is conserved, right? So you have the Z times Z is the number of protons. So you have a number of protons times the mass of a proton. This is the number of neutrons. So you have the number of neutrons times the mass of the neutron times c squared. Okay? So this is the mass of the separated nucleons. And you can see, right, that this, just like I said earlier, right, this is less than that because you have this additional binding energy. Okay, so, so how do you calculate the binding energy? Well, it's simple, right? You just take this minus that. Whoopee, Okay, so that's the binding energy, right? Just the mass of the separated nucleons minus the mass of the nucleus. And it's energy, so mc squared. So that's not a big deal. Okay, so if we want to use this formula, we have to know the mass of the nucleus, and we also have to know the mass of each element, right? Yeah. Okay? So we need nuclear masses. That's what I'm saying, right? We need nuclear masses. We already know what the mass of a proton and a neutron are, but we need the mass of the nucleus for every element, right? Well, that's not so bad. Big deal. You look it up, right? Well, hold on. So here's the back of the book. It says Atomic and Nuclear Data, Appendix C. Now look at here. All right, so we have atomic number, number of protons, element, symbol, mass number, right? So this is number of protons, mass number of protons and neutrons, atomic mass, percent abundance, all this stuff we don't know about yet. So what doesn't it have? It has atomic mass. I don't want atomic mass. I want nuclear mass, right? So the crummy Appendix C doesn't even have nuclear mass. Oh, man. So what's the difference between atomic mass and nuclear mass? Well, mass of the electrons. Agree? Mass of the electrons. Okay, no problem. We can work it out. We can work with these atomic masses. So here's this is what we're going to do. It works great. All right, so the binding energy again is mass of separated nucleons minus mass of nucleus. All right, so that's the same thing, right? Mass of separated nucleons, number of protons, mass proton, number of neutrons, mass neutron. All right, so we got it. But again, we don't know this because it's not in the book. Okay, so we just do a math trick, So right here, we're going to add the number of protons times the mass of an electron, right? In a neutral atom, you have the same number of protons as electrons. So here, we're going to add the mass of the electron times the number of electrons. And here, we're going to subtract it. All right, so we add it over here, we subtract it over here. Whoopee. So that's okay. Mathematically, we haven't cheated, right? We didn't cheat at all. Now, what's this? Well, this is Z. Just what's this? We can factor out the Z, and then we get mass of one proton plus mass of one electron. Well, what's that? That's a hydrogen atom, right? Hydrogen atom has one proton and one electron. So this here, this parentheses, is Z times the mass of a hydrogen. Got it. Then we have this, right? Okay, what's the mass of the nucleus plus Z times the mass of an electron? Well, this is the number of electrons in an atom, right, times the mass of an electron. So this is the mass of the atom. Hey, we're going to do it, right? Okay, so that's it. You add, you subtract, then you realize this is hydrogen, this is an atom, so now we can use our Appendix C. So that's totally awesome, right? Okay, now, again, we want to be smart about this. We don't want to goof around with joules and all that. And so we learned earlier that 1U equals 931.49 MeV per C squared, right? Well, that means multiply and divide. That means that C squared equals 931.49 MeV per U, right? So that's awesome. So we're going to, instead of writing C squared, we're just going to write this, 931.49 MeV per U. And then we're going to use these things in terms of U. And so the U here will cancel with the U here, and we'll get our binding energy in MeV. Isn't that nice and simple? So that's what we're going to do. And it works out super nice. Okay, let's quit because you're going to do an example next time.